So assignment 5, number 1 is again finding some intervals of convergence, stuff that we've done before, nothing new, right? So we're going to check these out first. They're going to be a little bit different in that this time what we're going to be doing is we're going to be seeing that these endpoints, I keep on writing 5, these endpoints don't always work out where one works and one doesn't work. They're a little bit different. So this series here has an n in the numerator, which is different for us, right? We haven't seen too many like that. So when we're determining interval convergence, our first step is to kind of do that ratio test, right? So I'm going to do that first. I'll be back in Flash. So that should be nothing new to you, right? We have the nth plus 1 term on top, the nth term on the bottom, and we have just done some fraction work, the complex fraction work, to kind of flip the stuff into 1. And then we get this 1, this goes to 1, right? N plus 1 over n, that goes to 1. This goes to n, this goes to what, 1/2. So then we're going to just have x over 2. And we say this must be less than 1 in order for this to converge, right? Rho has to be less than 1 for it to converge. So we can just say, okay, that must be this, and this is our interval. And we're like, yay, that's done. But of course, as we've said many times, we're not done. We're not done. Because what we have to do is we have to test our endpoints. So we come in here over here and put x equals -2 in here. We do x equals 2. And in this first one, we're going to get -2n over 2n. So we're getting an alternating series. Well, alternating series could conditionally converge, right? And here we just have 2 to the n over 2 to the n, right? 2 to the n over 2 to the n is just 1. So right away I want you folks to see that this is diverging by the divergence test, because the limit as n goes to infinity of a sub n doesn't equal 0. So this definitely diverges. So we're not going to have an equal sign over here. Now what about this one? Well, this one here is going to be alternating. So it's got the potential to conditionally converge, right? Alternating is good. But remember the first requirement. The first requirement after it's alternating is the fact that this needs to be approaching 0 as well. And this one, folks, is not. In fact, it's kind of it's alternating between negative and positive infinity with each term, and it is definitely not 0, right? So I had to have the not equal. So because they're not equal, they're both diverging. So that is our final answer. The endpoints both don't work. Now what about this guy? Oh, this one's pretty. A lot going on here. Okay, so as usual, I'm going to pull out the ratio test. See you in a second. Okay, so I kind of skipped right over to this one up here on the right side. I flipped everything. Please note, because the absolute value of this -1 part is unnecessary, I just left it in there. There's absolutely no need for it. You could take this -1 out, because the absolute value just says the negatives are irrelevant. But we can leave it in there. Technically, if you multiply this out, this is going to be 1, right? Because n to the 1/2, n to the 1/2, effectively, that's going to be 1 the same degree. If you really don't see that, you can multiply top and bottom by 1 over root n, and you'll hopefully then see that this limit is 1. So this is 1. This is going to be -1, effectively, and this is going to be x minus 3. So technically, it's going to be this. And for this to converge, we want that. So in order for this to all work out, we have to do a little bit of algebra. Subtract 3 from both sides. Divide -1 from both sides. When we divide it by negative, inequalities flip. And that's kind of written the wrong way. We don't write them this way, right? We kind of reverse the whole thing, and we'd write this interval like that. Okay, so we're between 2 and 4. Now, of course, we test those endpoints. Be back in Flash. Okay, so I just plugged in 2 and 4. When you plug in 2, you get -1 to the n, so that's why that's here. And when you plug in 4, you get 1 to the n. And that's why this 1 to the n is here. So we have 2 endpoints plugged in, and now we have to test each one. Now, if you look at this one over here, 1 to the n is just 1, so it's kind of like irrelevant. You don't really need that. And now we have something that's alternating, right? It's going from positive to negative, positive to negative. It's flipping back and forth every time. So this is an alternating series. An alternating series that looks like, hey, well, the denominator is getting bigger every term. It's alternating every time, right? if you put n goes to infinity, this is approaching 0. Like the 1 over the square root of n is approaching 0. And as n gets larger, each time the fraction is getting smaller. So it is getting closer and closer to 0. So it meets all requirements, right? It's alternating. The limit as n approaches infinity of a sub n equals 0. And a sub n plus 1 is always going to be less than a sub n. And therefore, this is converging conditionally. Yay! This is converging. We can come over here and say 4 works. We'll put a little equal sign right there. Now we have to check out this one. Well, this one over here, maybe this is going to converge too, right? Well, we have negative 1 to the 2n minus 1. And negative 1 to the 2n, folks, this is just, negative 1 squared to the n times negative 1 to the negative 1. And this, folks, is just negative 1 squared, just 1, right? I guess I need to write with 2 parentheses there, right? So that's just 1. So 1 to the n. This is just negative 1. So this series is not alternating. So we have to check for absolute convergence. It is not going to absolutely converge because by the p-test, we have a p that equals 1/2, which is less than 1. And therefore, we have a diverging series. So therefore, this is our final interval, final intervals from 2 is less than x, which is less than or equal to 4, because 2 works. 4 works, but 2 does not. It is a series that is not alternating and is not absolutely converging. And this one, I think we're going to say, wow, we've seen stuff like this before, and you're right. The only difference between what we've seen before on this one is the fact that we have this e in there. So it's in the numerator, where usually it's in the denominator. Okay, so I'm going to hit pause, do some work. You can do the same thing if you like, and we'll be back in a flash. So what do we have? Well, we have, again, a fraction with our ratio test. We're finding what rho is going to be. We're going to find out what values of rho are going to make this converge. This n plus 2 over n plus 1 is a little bit different, but it's still the same thing, folks. It's still approaching 1 as n goes to infinity. So now we're really going to just be left with xe. It's got to be less than 1. So therefore, xe has to be less than 1 and has to be greater than negative 1. We divide everything by e, we get our interval of convergence. Are we done? Of course we're not done. We have to plug in these 2 endpoints. So when x equals... So now what happens here is that this kind of gets fun. Because if you plug in, if you said, hey, if x is 1 over e, what does the numerator become? Well, if it's 1 over e to the n times e to the n, that just becomes 1 to the n. So 1 to the n over n plus 1. And this, folks, is going to diverge. Why is it going to diverge? Well, if you really had to go through the whole technical details, it's going to diverge by the limit comparison test. And you're going to compare it with 1 over n. So if you take 1 over n plus 1 and you divide it by 1 over n, you take the limit of that, you get 1, which is a non-zero constant. So therefore, that means these two are both going to converge or diverge together. And this is a harmonic, and the harmonic series does diverge. So this is going to diverge because it's kind of moving at the same speed as 1 over n. So this one doesn't work, so 1 over e doesn't work. So now we're going to come in and test negative 1 over e. Well, if you put a negative 1 over e, you're going to get negative 1 over e times e. That's negative 1. So you're going to get negative 1 to the n over n plus 1. Now, we know this is not going to absolutely converge. Why? Because that's this, right? That's the alternating version of this. And we know this one diverges. But does this conditionally converge? Well, 1, it's alternating. 2, the series does approach 0 as n gets really, really large. And 3, every time you add another n, the fraction 1 over n plus 1 gets smaller and smaller. So this conditionally converges by the alternating series test. It conditionally converges by the alternating series test. And therefore, we have a little equal sign there. Well, that's not right. That's great. We're going to move on to the last one. What we have here is x to the 2n plus 1. X to the 2n plus 1, that's new. this could offer a new challenge that we have not seen before. Let's see what happens. Well, we have to do this a little bit more challenging because we have to add the n has to become n plus 1, right? So we're going to do, can I get rid of the negative 1, folks? I'm just going to get rid of the negative 1 because we're doing the absolute value. I just want to focus on this part for now because the negative 1 doesn't matter in the absolute value. So I want to focus on this. We have 2n plus 1, right? That's the next term. That's term a sub n plus 1. Again, the absolute value means that the negative I don't have to worry about. And now that the term that we had was 2n plus 1 over 2n plus 1, right? So, okay, it's a little bit different. So what do we have now? Well, we're going to have x to the 2n plus 3 over x to the 2n plus 1. And then we're going to have 2n plus 1 over 2n plus 3. Well, this is just 2 over 2 as n goes to infinity, folks. So this is going to be 1 again. What does this turn into? I got rid of the absolute value bars. Why did I get rid of the absolute value bars? Because x squared is always positive. So rho is going to be x squared. We want this to be less than 1. We just want x squared to be less than 1. When is x squared going to be less than 1? Well, you know, technically, you really should do this, right? Technically. You can set up your number line if you'd like. But most of us don't need to do this, right? Most of us don't need to kind of see that fact that this is where it's going to work, right? That's the correct zone. Most of us can see the fact this is going to be between 1 and negative 1. So we plugged in negative 1, and we plugged in 1. So x equals negative 1, x equals 1. We're plugging that in, and when we plug in 1, we're going to get negative 1 to the n here because it's alternating, and this is 1 to the 2n plus 1, so that's just 1. So you see I left that out, that 1 to the 2n plus 1 I just left out. Folks, this is an alternating series, and it's an alternating series that is going to converge conditionally. It's going to converge conditionally because 2n plus 1 keeps on getting really, really large, so therefore each term is getting subsequently it's getting smaller and smaller, and the term 1 over 2n plus 1 is approaching 0. So this does conditionally converge by the alternating series test. And now I need to think about this one. So we know this one works. What about this? Well, this numerator's a mess, right? Negative 1 to the 3n plus 1. What is that doing? Well, I think we can do this. I'm just focused on the numerator here. Okay, you with me? And then I can do this. At the end of the day, why am I doing this, right? I'm just trying to figure out whether or not this is going to alternate. Because if it's going to alternate, we know it's going to conditionally converge. Negative 1 cubed is negative 1. Which just equals negative 1 to the n plus 1. Which means every time I add 1, it's alternating signs, right? If I put 1 in there, it's even. If I put in 2 there, it's odd. It's alternating every time. So this too is going to conditionally converge. We have both sides are going to converge conditionally because both of them are alternating series that are approaching 0, that are getting smaller every time, and they're alternating every term because we just showed that by doing a little bit of exponent algebra. So there's our final answer in an interval of convergence that has both endpoints that actually converge. All right, folks, see you next time.